It is 2 in the morning somewhere in the middle of the Caribbean. The nearest land is a couple hundred miles away in any direction. And on this ship, right now, 6,000 people are asleep in air-conditioned cabins. The ice rink on Deck 7 is being resurfaced. The bakery is running. 3 separate HVAC systems are quietly managing the temperature across 18 decks. The navigation bridge is lit. The elevators are ready. The pools are heated and filtered. Hot water is available in every cabin, on demand, instantly. Nobody on board is thinking about any of this. That is the point. But here's the question nobody asks while they are refilling their drink and watching the ocean. Where is all that electricity coming from? The honest answer is not what most people picture. There is no cable trailing behind the ship. There is no connection to any grid. There is no shore, no substation, no infrastructure within 200 miles. Everything you see, every light, every screen, every blender in every bar, every refrigerator in every kitchen, is being powered by a system this ship built entirely for itself. A system running right now, deep in the hull, out of sight, without interruption. This is not a ship that uses electricity. This is a power station that happens to float. Most people, if they think about it at all, imagine something like a very large car engine. A big diesel somewhere in the bottom, turning a shaft, turning a propeller, moving the ship. Maybe some of that mechanical power gets siphoned off to run the lights. The same basic logic as a generator on a camping trip, just scaled up. That mental model is wrong. Not slightly wrong, fundamentally wrong. And the gap between what people imagine and what is actually happening tells you something important about how modern engineering solves problems that cannot be solved the obvious way. Start with the constraint. A large cruise ship is not one thing. It is many things operating simultaneously, each with completely different power demands. It is a hotel with 5,000 rooms. It is a hospital with a full medical unit. It is a food operation running multiple restaurants, a buffet, dozens of bars, and a bakery producing thousands of items a night. It is a water treatment plant making its own fresh water from the ocean. It is a waste processing facility. It is a theater. It is a theme park. And somewhere underneath all of that, it is also a vessel that needs to move. A single mechanical drivetrain cannot serve all of those things at once. The demand is not consistent, not predictable, and not manageable through simple mechanical power distribution. At 8 in the morning, thousands of passengers are taking showers simultaneously. The breakfast kitchens are at full load, and the ship is cruising at speed. At 3 in the morning, most of that load disappears. The system powering a dinner service for 7,000 people needs to be able to dial itself back to a night configuration and then scale up again by 6 a.m. without stalling, surging, or failing. Mechanical drivetrains cannot do that. Electric systems can. This is why every major cruise ship built in the last few decades runs on what engineers call diesel-electric architecture. The diesel engines do not turn the propellers. They turn generators. The generators produce electricity. That electricity flows into a shared internal grid, and everything on the ship, propulsion included, draws from that grid. The engines are not the power system. The engines feed the power system. The power system is what actually runs the ship. There are typically 4 to 6 generator sets running simultaneously on a large cruise ship, each one the size of a small house, producing tens of megawatts individually. Together, at full operation, they can supply somewhere between 50 and 75 megawatts of total electrical capacity. To put that in context, that is roughly the electricity consumption of a small city, 50,000 homes. Running from machines buried in the hull of a single vessel continuously for the duration of a 7-day voyage. None of those engines can be allowed to fail completely. This is where redundancy becomes a survival requirement, not a design preference. The ship is not near anything. If power goes wrong in the middle of the Atlantic, there is no grid to fall back on, no utility company to call, no backup arriving in 20 minutes. The redundancy has to be built in from the start. Multiple generators, multiple fuel lines, multiple switchboards, systems designed so that losing one unit does not cascade into losing everything. Running the generators is one problem. Managing what they produce is another problem entirely. Every ship of this class uses a power management system, software that monitors the total electrical demand across the ship in real time, balances load across the active generators, and automatically brings additional units online or takes them offline, depending on what is needed. It sounds mechanical. The reality is closer to what a grid operator does for a regional power network, except it is happening inside a single vessel adjusting to moment-by-moment changes with no room for error. When the main theater runs a full evening show, that is a significant electrical event. lighting rigs, sound systems, stage machinery, a full audience with their own ambient needs. All of it lands on the grid at once. The power management system sees that coming. When dinner service on 4 restaurants peaks simultaneously, the system adjusts. When the ship accelerates to make up time lost to weather, propulsion demand spikes and the system responds. All of it happens automatically, invisibly in real time. Now here is where the story gets genuinely strange. Most people assume that when a ship moves through the water somewhere in the engine room, a large shaft is spinning, connected directly to the propeller. That is how ships worked for most of maritime history. Turn the engine, turn the shaft, turn the propeller, move the ship. Modern cruise ships do not work that way. The propellers on a large cruise ship are electric motors, not mechanically connected to the engines, not driven by a shaft running the length of the hull. Electric motors, powered by the same grid that powers the ice rink and the bakery and the air conditioning. The engines generate electricity. The electricity moves the ship. The propellers are, in the most literal sense, just another load on the grid. This architecture produces a consequence that almost nobody on board understands. The machinery moving the ship and the machinery running your cabin, television are the same system. They compete for the same electrons. They are managed by the same software. When the ship needs to accelerate, the power management system is making decisions that affect, at some marginal level, every other electrical load on board. The propulsion units themselves, called azipods on many modern ships, are worth understanding. They are not fixed to the hull in the traditional sense. They are rotating pods mounted underneath the ship, each containing an electric motor directly connected to a propeller. The entire pod can rotate 360 degrees. There is no rudder. There is no long drive shaft running through the hull. The ship steers by, pointing the motor in the direction it wants to go. This matters for reasons beyond elegance. A traditional shaft-driven ship coming into a tight port needs tugboats to push and rotate it into position, because the fixed propellers and rudder cannot produce the lateral force required for precise docking. An azipod-equipped ship can move sideways. It can rotate in place. It can hold a precise position against wind and current without any external assistance. The flexibility of electric propulsion does not just change how the ship moves through open water. It changes what the ship can do when it arrives. Meanwhile, back to the grid. Here is the second twist, and it is less intuitive than the first. The power consumed by passengers simply existing on the ship. Air conditioning, hot water, lighting, elevators, food service, entertainment systems regularly equals or exceeds the power used to actually propel the vessel through the ocean. The vacation experience itself is as electrically demanding as the engines that move the ship. This category is called hotel load, and it is not a minor afterthought. It is half the ship's electrical budget, sometimes more. Every cabin is air-conditioned individually. Every restaurant runs commercial-grade kitchen equipment. The water parks, the pools, the spas, the theaters, the retail spaces, the crew quarters, all of it draws from the same grid as the propulsion. When engineers are calculating how many generators a ship needs, the guests themselves are a major variable in the equation. The engines produce heat as well as electricity, and the ship has learned not to waste it. Exhaust from the diesel generators leaves those engines at extremely high temperatures. On most large cruise ships, that exhaust is routed through heat recovery systems that capture the thermal energy and convert it into steam. That steam heats water. It supplies the laundry systems. On some ships, it drives secondary turbines that feed additional electricity back into the grid. The ship is recycling its own waste energy, quietly and continuously, in a system most passengers will never know exists. Then there is water. A large cruise ship produces its own fresh water, not symbolically, hundreds of tons of drinking water per day, manufactured from the ocean through a combination of reverse osmosis membranes and thermal evaporation systems. Those systems run on electricity. The water you drink, the water in your shower, the water in the pools. All of it was seawater recently, processed through electrically driven machinery running below the waterline. The ocean is both the medium the ship travels through and the raw material it consumes. Fuel is the foundation of everything, and the scale of consumption is difficult to absorb. A large cruise ship running on heavy fuel oil burns somewhere between 200 and 300 tons of fuel per day, not gallons, tons. The fuel tanks, the piping systems, the transfer pumps, the treatment systems that clean the fuel before it reaches the engines, all of it constitutes a hidden infrastructure inside the hull that most passengers never consider and never see. The industry is changing. In 2018, a ship called Aida Nova entered service as the first cruise ship fully powered by liquefied natural gas. LNG burns cleaner than heavy fuel oil in several meaningful ways. producing less sulfur dioxide and particulate matter. But switching to LNG is not simply a matter of changing the fuel. LNG must be stored in cryogenic tanks at approximately -160 degrees Celsius. It requires different bunkering infrastructure, different safety systems, different handling protocols. The ships must be redesigned from their internal architecture outward. Newer vessels are being built to accommodate it. The industry is in the middle of a transition that is more like rebuilding the engine room from the inside out than switching to a different grade of gasoline. At certain ports, ships can connect to the local electrical grid and shut their generators down entirely. Cold ironing, the practice is called. The ship plugs in, the diesels go quiet, and the port's electricity powers the vessel while it is docked. It reduces emissions significantly in the port environment. In practice, it is still uncommon. The infrastructure required on the port side is expensive. The power capacity many ports can offer does not match what a modern cruise ship consumes, and the commercial and regulatory frameworks that would make cold ironing routine are still developing. It is a real solution. It is also a partial one, unevenly applied. Pull back now from all the mechanisms. 6,000 people on that ship will wake up tomorrow morning with no awareness of any of this. They will take hot showers, order eggs, ride elevators, watch shows, complain if the air conditioning is slightly off, and photograph the sunset from the deck. The system is working as designed. The invisibility of it is not a side effect. The invisibility is the product. The entire passenger experience has been engineered around the idea that you should never have to think about where any of this comes from. That design principle is not unique to cruise ships. It is the principle behind most of the comfortable infrastructure modern life runs on. The surfaces that feel effortless are almost always downstream of something enormous, unglamorous, and invisibly coordinated. The comfortable thing and the engineered thing are always the same thing, you just rarely see both at once. But on a cruise ship, floating alone in international waters, manufacturing its own power and its own water, and managing a grid the size of a small city, the two things are unusually close together. Below the waterline, a floating power station running continuously, automatically with no margin for failure. Above it, a water slide, a steakhouse, a casino, a spa. The most impressive thing about a cruise ship is not the atrium. It is not the ice rink or the water park or the 18 restaurants. It is that you spent 7 days being powered by an industrial power plant and you never once thought about it, not for a second. That forgetting was not accidental, it was the whole design.